Hello and welcome. I'm here, yes I know, I'm not very big. My name is Andy. I am an Italian agile frog, a protected species, and I have been living here for so long that I know this place really well. Today I would like to tell you about nuclear decommissioning. That's our pond. Do you like it? It is located in Ispra, a small town in the north of Italy, close to Milan. Have a good look, I'm going to show something to you. Ready? That's it, the Ispra JRC site, a joint research center of the European Commission. It all began back in 1957, when the site was chosen for Italian nuclear research. Then in 1960 it became part of the Euratom program for European nuclear research. There are three types of nuclear facilities here. First of all, we have those that produce artificial radioactivity, 2 experimental nuclear reactors, and a particle accelerator. Then, there are 3 laboratories that test and study the radioactive samples produced by the reactors. Voila! And lastly, the waste management facilities. Such plants are always necessary for a smooth and safe operation of any nuclear center. There are 2 of them, plus the ISF, Interim Storage Facility, a temporary construction. Here they are. And that is how the Euratom Center was born. But eventually, the research on nuclear reactors has come to an end, while new research needs arose in other fields. The advent of the digital age, with computer simulations, contributed to the decision to convert the site to non-nuclear purposes. This is why, in 1999, the nuclear decommissioning program started. Decommissioning means to remove all the material that was contaminated during operation, and to concentrate all the radioactivity in special waste containers. But before I get into the details of this process, let's go over what we know about radioactivity. Radioactivity is a natural phenomenon. You can't see it, but it's all around us. To put it simply, radioactivity is a type of radiation that is emitted by unstable atoms. And since everything is made up of atoms, that means plants, rocks, even the air we breathe, everything is a little radioactive. Let me elaborate on that. Look above the map. May I introduce you to an atom? It's a tiny invisible particle of any matter. In the middle of it is nucleus, composed of neutrons and protons, and it's orbited by electrons. Sometimes though, the nucleus is unstable. The atoms with unstable nuclei are called radionuclides. They get rid of excessive energy in the form of particles emitted from that unstable nucleus. Depending on the particles emitted, we recognize 3 kinds of radiation: alpha, beta and gamma. Look at your hand, what you see is an instrument for measurement of radioactivity. Now you can use it. Go ahead, move around and measure the different types of radiations of the atom. The readings change according to the distance and the type of emission. Excellent. Alpha and beta radiation can be blocked by a thin layer of liquid or solid material, like this metal drum for example. Even the air, with adequate distance, is enough to block them. Gamma radiation, on the other hand, has rays which penetrate deeply into materials, which means that, even when gamma radionuclides are enclosed in a drum, they can still be measured very easily outside. Let's add a lead wall. You can see that gamma rays cannot get through thick layer of lead. Therefore, lead is widely used material to shield gamma radiation. Perfect. We're ready for the next part. We'll start with the first stage of the decommissioning, the plant characterization, or in other words, the description and inventory of the nuclear facility. It is a really important process that will affect all subsequent stages. Let's go and see more closely the ESSOR reactor. The aim here is to collect any information available on all the elements which make up the plant. As this is a digital age, the information is stored in a smart digital database. Right then, this cube is a representation of the digital database created specifically for this project. As you can see, for the moment it's empty, but it's going to fill up as the decommissioning project progresses. To begin with, all the historical documents in the archives are catalogued and digitalized. The first information comes from the initial documentation, drawn up when the reactor was built, and from the operation and maintenance records. Using this documentation, it is possible to make a list of all the parts and components which will be dismantled. In this room, adjacent to the ESSOR reactor vessel, you can see for example one of the 3 reactor cooling systems. It's made up of the water circuit which used to cool the nuclear fuel by means of a heat exchanger and some auxiliary components. Help me register the inventory of this room. We are looking for all the physical information of each component. Look at your hand again. With the scanner that has just arrived in your hand, scan each element of the cooling circuit by pointing at it with the laser for 3 seconds. Right. When you're ready, send the information to the digital database by pressing the Send button. Nearly there, just another 2. Right. When you're and the last one. Right. When you're ready, send the information to the digital database by pressing the Send button. Everything's scanned. Now that's what I call a teamwork. Now is important to index all the elements into what we call homogeneous groups. What are they? In simplified terms, a homogeneous group is made up of components with the same ratio of alpha, beta and gamma contamination. And for accurate ratios between alpha, beta and gamma, destructive analyses of some material samples are required. Let's go to one of the facilities on the site, called EcoFerro. Samples of the components are extracted and submitted for advanced radiological tests in the laboratories. All 3 types of radioactivity, alpha, beta and gamma, are measured, and the correlation between gamma and the other 2 types can be determined. Keep this in mind because this proportion between gamma and alpha, beta will be used later. Excellent. By this, the process of the plant characterization is finished. All the components are assigned to homogeneous groups and must not be mixed up subsequently, for the entire duration of the process. Let's move on to the second step. As with any industrial project, engineering is present all along the decommissioning process lifetime. Let's take a look inside the engineer's offices. Using the information from the database and available to all the stakeholders, the project is planned in detail, from the actual dismantling, through waste management, to the full cleanup of the site, turning it into what is called a green field. What you can see here is the creation of the decommissioning plan. The plan defines exactly what has to be removed, how and in which order. Then safety analysis is performed and protection systems are defined. Everything is planned paying attention to safety, environmental protection, quality, costs, and human resources. Once the plans are set and documented, the proposal is submitted to various authorities, both local and national, namely for environmental protection and nuclear safety. Well, that certainly took a lot of work, but the plan has been approved. And now the third step, the actual dismantling, can finally begin. Come with me and we'll see how things are getting on in the ESSOR reactor. First of all, the facility is being prepared for the work to be done, step by step, zone by zone. This is how the workyard is prepared. Enclosing the perimeter is the first task. Then all the residual liquids are drained from tanks and pipes. The electricity is disconnected and an autonomous power system is set up. Airlocks and local ventilation systems are installed. If necessary, concrete or even lead walls are erected to protect workers from radiation. Lastly, 2 buffer storage areas are created, one for radioactive waste and one for clearable material. Clearable means material not contaminated which must undergo exit checks. When the reactor was operational, the contamination was already contained in hermetically sealed circuits. This is why most of the material in the nuclear facility is not contaminated. During the dismantling phase, besides paying attention to the homogeneous groups, there is another golden rule: the components must be removed in the order from the cleanest to the most contaminated. With this precaution, 90% of the material can be defined as clearable, uncontaminated. Waste traceability and its physical and radiological characterization are fundamental. Each drum and container, once filled and sealed, is catalogued and labeled, while the content is described, photographed and measured. And here is the machine used to measure the radiation coming from inside the drums. It is called gamma spectrometer and measures precisely all gamma radiation. Since we maintained the homogeneous groups, we can calculate alpha and beta radiation by measuring only the gamma radiation. Do you still remember that we established the ratios earlier? The characterized drums will now be removed from the ESSOR reactor site and sent to Area 40, Tokita, with their completed and approved dossiers. You've got a scanner in your hand again. Look at the drum that I am sitting on and try to be the first person to scan the barcode for 3 seconds. Come on, look for the barcode on this drum and scan it with your scanner. There you go, you now have access to all the information about this specific drum. Let's move again to pay a visit to the Area 40. Here is where the next phase happens. I'm talking about the waste management. This is the stage where the mass and the volume of the radioactive waste are reduced as much as possible. After that, final waste packages are created in processes called waste conditioning, and they are stored temporarily. But first things first, all the drums arriving to Area 40 are directed to dedicated facilities, or even to off-site services in others' nuclear sites, depending on the type of treatment they require. I'll now talk you through the 4 treatments that the waste goes through. The first one is supercompaction. A drum full of soft, compactable waste is put into a hydraulic press and then compressed into so-called packages. This reduces its volume by up to 70%. You see, the database is updated all the time. Now on to metal melting. With this process, mass of metal waste can be reduced by 90%. During the melting process, all radioactive contamination is separated from the metal, which can be then recycled. Slag and the filters that collected all the contaminants are stored in new drums. These drums have to be characterized again. And of course the database is updated with these new data. And now incineration. Some flammable waste is burned in special incinerators, reducing its mass by 70%. All the radioactivity is not lost but is concentrated in the ashes and filters, which are collected and confined in new drums. These also must be characterized. And the database is updated again, as always. The last treatment is reserved for liquid waste. Here, special filters separate radionuclides from clean water, which can be released into the environment after the final check. All radioactivity is concentrated in radioactive sludge, which is collected into drums. Since it's not allowed to dispose of liquids as it is not safe, sludge is turned into solid waste by admixing it into cement. Overall, liquid treatment is very effective and reduces the volume of the waste by 99%. Now when the mass and volume of the radioactive waste is concentrated and reduced, all post-treatment products are encapsulated in large steel containers, called CP5.2. To immobilize the waste inside these containers, a special cement is poured into them to fully encapsulate the waste in the middle. The CP5.2 containers filled with radioactive waste and cement are called final waste packages, and they are designed to be buried underground. A brand new interim storage facility is ready and waiting for them. Its objective is to store centrally final waste packages from entire Ispra site for a few years before they will be moved to the Italian National Repository for final disposal. Just to give you an idea, all of the radioactivity of the 8 nuclear facilities of the Ispra site will fit into around 1,000 final waste packages. Let's come back up for some air. Now that all the interior equipment has been taken out, and that all the radioactivity has been eliminated, it's time for the final survey of the buildings and terrain. This transition phase, between a site that was in nuclear use and one that can go back to conventional purposes, will take a number of years in which a lot of measurements and analyses are made. The first task is to check for the complete absence of radioactivity. The entire site is scanned across the board. Once declared clean, the buildings can be demolished or refurbished for a different purpose. The monitoring of buildings and terrain left behind the former nuclear facility continues for another 5 years. And we are done. The whole area is completely reusable. Once the Italian National Repository gives its authorization, all final waste packages will be relocated there along with their corresponding information dossiers represented by the little red cube inside the database. Take a look at it. The interim storage facility will be demolished and the entire Ispra site, now completely clean, is considered green field. Over the coming years, many sites similar to this one are going to be decommissioned. A huge market is opening up in Europe devoted to nuclear decommissioning. You can imagine the number of engineers, physicists, workers, scientists and other amazing professions who will be involved in a program of this scope. Maybe one day, you will be part of it, too. And that's all. Farewell, dear visitors. Thank you all for your attention. Do not hesitate to return to JRC Ispra. You will find an exhibition on nuclear decommissioning with an educational path. You can make an immersive visit to all our installations, and there will also be a virtual assistant who will answer all your questions. I will wait for you and show you my pond. You do swim, right?